Hi everybody! In this video, we are going to talk a lot about something called Ksp. Ksp is also known as the solubility product constant. The Ksp describes the equilibrium established by the aqueous form of a solid, and this is usually ions. The reaction of Ksp describes a solid becoming aqueous. This is usually used for salts. So for example, sodium chloride, the solid, is becoming aqueous and splitting up. And that's what Ksp stands for. So the K of this reaction would be the Ksp. Now, this is related to solubility because only a maximum amount of solid will turn into its aqueous form, as you will see soon. So the Ksp is equal to the concentration of essentially the products, since the reactants are always solids and solids are not in the equilibrium expression. So because of that, Ksp is equal to the concentration of sodium ions times the concentration of chloride ions. And in this case, it seems like the Ksp of sodium chloride is 37 at 25 degrees Celsius. So this essentially tells you how much you can dissolve before you hit a cap. So for example, it will tell you how much Na plus and how much Cl minus you can have in the solution. And once you hit 37, or when the concentration of Na plus and Cl minus multiply out to be 37, then you've hit your cap and you cannot dissolve anymore. So it's a nice way to think about things. And now let's actually talk about more things. So in general, a high Ksp means that the solid is very soluble because there's a high product to reactant ratio, aka lots of products or dissolved solids. So if we have lots of this stuff, that means that we can dissolve a lot. Now what about the opposite? What if we have a low Ksp? Well, a low Ksp means that the solid is not very soluble. And this is because a low Ksp means a low product to reactant ratio, or in other words, there aren't that many products, which means that if you don't have that much of the products, that means that you're not going to dissolve very well, which is why a low Ksp corresponds to something that is not very soluble. Now before we look at the graph, let's take a look at the dissociation of silver chloride into its ions. So it's turning from solid to aqueous, and thus we can find a Ksp. So the Ksp of silver chloride is actually 1.8 times 10 to the negative 10. But if you want to write the expression, you do products over reactants, and we just have Ag plus and Cl minus. And how do we graph this? Why is it a curve? Well, we see that X will be our chloride concentration, and our Y will be our silver plus concentration, and this is equal to C, a constant, or in other words, our Ksp. Now, in your math class, you've probably learned that X times Y equals constant is an inverse graph where it kind of looks like that. But in this case, we are going to ignore quadrant 3, which is this quadrant, simply because we never have negative concentrations. So we focus on this curve, and this is exactly what is shown in this graph up here. So note the relationship, and this is when Ksp is equal to the Ag plus concentration times the Cl minus concentration. So notice how along this curve, Q will equal Ksp, because along this curve, the silver concentration and the chloride concentration multiply up to equal this number, which turns out to be the Ksp. So when Q equals Ksp, you are along this curve because you have just the right number of chloride ions and silver ions to have the Q be equal to the Ksp. Now, what if you have too many silver or chloride ions? For example, if you're at this point over here shown in red, if you're here, this means that you're not on the curve, which means that the Q here will be greater than the Ksp. And when the Q is greater than the Ksp, as shown here, our reaction will actually go backwards, and our ions will revert back to the solid form, or in other words, they will precipitate. So when we have too many products or dissolved stuff, and in this case, the dissolved stuff is Cl- and Ag+, our reaction will go backwards and it will undissolve the stuff, or in other words, it will precipitate out of the solution. And on this point right here, this is where supersaturation occurs, because supersaturation occurs when there is too much stuff dissolved and when you're not on the equilibrium curve. And remember, when Q equals Ksp, that's the maximum amount of ions that can be in solution. And if you go beyond that, you're essentially going over the saturation point and becoming supersaturated. And when supersaturation occurs, the reaction wants to go backwards to remove some of these excess ions in order to get the system back into equilibrium. Now, what about when Q is less than Ksp? Or in other words, when the product between the two ions is less than the Ksp? Well, over here, you can actually dissolve more because you have some space left over, since you haven't reached our Ksp yet, which, remember, is the cap for the maximum amount of ions that can dissolve. So, since Q is less than Ksp, the reaction will move forwards and the silver chloride solid will dissociate into its respective ions. Now, this occurs, of course, when Q is less than Ksp, or when there are too few products or dissolved stuff. And when there are too few products, or in other words, it is an unsaturated solution, then the reaction continues to dissolve the solid, or our reactant, until it runs out or it reaches equilibrium. Sometimes, if there isn't enough solid to dissolve, the reaction may never reach equilibrium. So if you're at a point like over here, this means that Q is less than Ksp, and that means that you're not at equilibrium. And if you have no more solid at that point, then that means that you'll stay at that point. But if you happen to have more silver chloride, then you can keep on dissolving silver chloride until you reach equilibrium. So as you dissolve silver chloride, our silver concentration and our chloride concentration will increase. And for every one that the chloride increases, silver will increase by 1 as well. Since if we think about it, when silver chloride dissociates, it dissociates in a 1-to-1 ratio. So for every 1 Ag+, there will be 1 Cl-, and it will move up until it hits the curve. And once it hits the curve, the balance between Ag+ and Cl- will be fulfilled, and the system will have reached equilibrium. So now let's talk about the math. Let's try to find the molar solubility, or in other words, the maximum amount of salt that can dissolve in M. If the Ksp of calcium phosphate, which is a fertilizer compound by the way, is 1 × 10⁻³ well, we can write our reaction for Ksp by having this solid. So this solid is calcium phosphate, and I balanced out the ions so that the charges cancel out, and it dissociates into 3 calcium ions and 2 phosphate ions, and they're both aqueous. So our Ksp is equal to the concentration of calcium ions cubed times the concentration of phosphate ions squared, because remember, we're looking at the coefficients. So now let's calculate the Q in order to figure out which direction this reaction moves. So right at the beginning, we are dissolving this in water because Ksp usually refers to water. So we're dissolving this in pure water, and we know that initially there's nothing in the pure water. So because of that, our initial concentration of calcium and phosphate are both 0. So Q will start off at 0, and thus Q will be less than K because 0 is less than 1 × 10⁻³ And because of this, the reaction will move forwards. So we know that initially no solid is dissolved in the pure water. So we assume that there is an unlimited amount of calcium phosphate solid, so let me write solid there, since you are saturating the solution until it reaches the solubility cap, because we are trying to find the molar solubility, or the maximum amount of salt that can dissolve. So you want to max it out to the point where it reaches equilibrium, because remember, at equilibrium, that's when the solution is considered to be saturated, or when there's a maximum amount of salt that is dissolved. So let me remind you again that everything that's on this curve will be at equilibrium, or in other words, the maximum amount of ions is dissolved at equilibrium. So just keep a note of that, and knowing that, all we have to do is to make the system go to equilibrium in order to get our maximum solubility, or the maximum amount of salt that can dissolve. So here's the reaction, and here's an ice table or ice chart. So we start off with lots of salt, and as you'll see later, since this is not part of the equilibrium expression, we ignore this part because it's not very important. And we know that for every x molar of solid that is dissolved, so that's why I'm doing minus x, then 3x molar of calcium ions will be produced, and 2x molar of phosphate ions will be produced. So I'm following the stoichiometry. Just keep a note of that. And in the end, we still have lots of salt, and we don't care about this, by the way, so we ignore the solid column, and we have 3x and 2x for the expressions for the concentrations of calcium 2+ and phosphate respectively. So we can set the Ksp equal to the expression, and we plug in 3x for our calcium 2+ and the 2x for our phosphate, and we kind of simplify things, and we get that 1 times 10 to the negative 33 is equal to 108x to the 5th. So we kind of just solve for x, and we get that x is 1 times 10 to the negative 7 after applying sig figs. So if you remember, x is the molarity of salt that was dissolved. Therefore, the molar solubility of calcium phosphate is equal to x, or in other words, the molar solubility of calcium phosphate is around 1 times 10 to the negative 7 molar. And if that didn't make sense to you, let's think about it another way. We know that x is this, so since 3x is the concentration of calcium ions, then that means that the concentration of calcium ions is going to be 3 times 10 to the negative 7 molar. And we can use some cool stoichiometry to figure out the molarity of the salt. So for every 1 molar of calcium phosphate, there are 3 molar of calcium ions that are produced from it, since there are 3 calciums in 1 calcium phosphate. So doing the math, we get that the molar concentration of calcium phosphate in a saturated solution is equal to this, and that's the same thing as the molar solubility, since the concentration of a saturated solution is equal to the solubility of it, since those two represent the maximum amount of salt that can be dissolved. So we have an answer to this, and that's cool. So what happens if we compare Ksp to figure out which salt is more soluble? So the thing is, you can only compare the Ksp of 2 salts with the same I value to see which one is more soluble. Meanwhile, you cannot compare the Ksp of 2 salts with different I values. This is because for salts that split into many ions, for example I equals 5, you are taking numbers to larger powers, and this can cause the Ksp for salts with high I values to be super small or super large depending on what the concentration is. Meanwhile, for something like I equals 2, you might be taking things only to the first power, because for I equals 2, for example, sodium chloride becomes sodium plus and Cl minus, and let me put a double arrow there. So the Ksp for something with I equals 2 would equal, well, let's see, it would equal sodium plus, of course, and Cl minus. But for something like calcium phosphate, notice how you're taking them to very large powers, and this can drastically affect the results. So maybe the 2 salts can have the same solubility, but their Ksps can be so different just because of the fact that you're taking things to the 3rd power here, while you're taking things to the 1st power here. So in general, if the I values are different and you still want to compare the solubilities of the 2 salts, then you need to calculate it by hand, as I did in the previous question. So let's play around with units, and let's try to solve this question. So lead 2 iodide has a solubility of 0.0756 grams per 100 milliliters of solution in water, at 20 degrees Celsius. Calculate the molar solubility and the Ksp of lead 2 iodide at 20 degrees Celsius. So I should write that. And the first thing I would do is try to convert the solubility into molarity, since we need the molar solubility and not just the solubility. So to get the molar solubility, we have to, of course, get moles over liters of solution, and right now we have grams over 100 mLs of solution. So we have to do some math. So I want to cancel out mLs, and I know that for every 1,000 milliliters, we have 1 liter. And I also know the molar mass of lead 2 iodide. I could simply look at a periodic table, and I calculate it to be this. And multiplying it all out, we cancel out the grams and cancel out the mLs, and we divide this by 100, multiply it by 1,000, and divide it by 461.00, and we get our units as moles per liter, and this is the same thing as molarity. So, in the end, the molarity will be 1.64 times 10 to the negative third. Or in other words, the molar solubility of lead 2 iodide is 1.64 times 10 to the negative third molar. Now, we know that the Ksp is going to be equal to Pb2 plus times I minus squared, based on the reaction we wrote down here. So if we want the Ksp, we need the concentration of lead 2 plus and I minus. How do we get those? Well, we do have the concentration of PbI2 in solution, so we could use some stoichiometry and figure this out. For every 1 molar of PbI2 dissolved, we have 1 molar of Pb2 plus because there's only one of them. But for every 1 molar of PbI2, we have 2 molar of I minus, as expressed by I2, or 2 I minuses in the salt. So I will have 1.64 times 10 to the negative third molar of lead 2, and I will have twice as many molar of I minus, or 3.28 times 10 to the negative third molar of I minus. And I simply chug these into the equation I wrote up here, and you do the math, and I get that the Ksp for lead 2 iodide turns out to be 1.8 times 10 to the negative 8. And I forgot to do sig figs, but the actual answer is 1.76 times 10 to the negative 8, since there are 3 sig figs here and 3 sig figs here. So I didn't watch out for that, and that was kind of scary. So this is the real answer, and the actual value at 25 degrees Celsius is 1.4 times 10 to the negative 8. So we're pretty close by doing this math, and that's cool. So let's actually look at something called the common ion effect. The common ion effect occurs when the ion that is a part of your Ksp is already part of the solution before you even added any solid. So, because of this, the solubility of the salt decreases. So, all in all, an ionic solid is less soluble if there is a common ion in the solution. So let's do an example. The Ksp of copper 2 chromate is 3.6 times 10 to the negative 6 at 25 degrees Celsius. Find the molar solubility of the salt in a 0.100 molar solution of copper 2 nitrate. So, as you can see, we have 0.1 molar of copper 2 nitrate, and we know that for every 1 molar of copper 2 nitrate, there is 1 molar of copper 2. So because of this, for every 0.1 molar of copper 2 nitrate, this must mean that we have 0.1 molar of copper 2 in the solution. So this will be considered our initial conditions. And we could now write the dissociation of copper 2 chromate into its respective ions. So if you don't know your ions, go ahead and review that and come back to this video. Now, if you do know your ions, let's keep on going. So we could calculate the Q so far. So the Q is equal to the expression for a Ksp. It's going to be the concentration of copper 2 times the concentration of chromate. So the concentration of copper 2, as we said, was 0.100 molar, and the initial concentration of chromate is 0 because nothing dissolved initially except for the fact that we had 0.1 molar of copper 2 nitrate. So 0.1 times 0 is 0. So Q is less than K, so our reaction will go forward. Now let's actually make an ice table now. So we don't care about how much copper 2 chromate solid there is. We care about the ion concentration since those are used in our Ksp. So we know that we start off with 0.1 molar of copper 2, but we start off with no chromate. So for every X molar of copper 2 chromate that dissolves or disappears from its solid form, 0.1 molar of copper 2 and 0.1 molar of chromate are formed by a stoichiometric manner. So you see how it's all a 1:1:1 ratio. So that's why it's a 1:1:1 ratio. Now doing the math, you get that the expression for the equilibrium concentration of copper 2 is going to be 0.1 plus X. And for chromate at equilibrium, the concentration is going to be X. So we have our equilibrium concentrations and we can chug them into the Ksp. And we move things around and we simplify things. And then we move things around again to get a quadratic expression. And we use the quadratic formula to solve for X when everything is set to 0. So all this is what we need to figure out. And on the next slide, I will teach you how to keep track of your sig figs very carefully. So remember, chemistry is also math. So this is the quadratic that we need to solve, and I want to make sure that I am accounting for sig figs. So I simplify this to get this, and then I add these two together, and I'm keeping a lot of extra digits. So a good tip, as said in the previous part, is to keep as many digits as possible because sig figs can come later. And in this case, since we're dealing with such tiny numbers, every digit matters. So you want to make sure that you're keeping as many digits as possible. Now, you see how I added it, and I kept track of sig figs, and I took the square root of it, and then I came up with 2 answers. So each of these had 3 sig figs in the end, and they're pretty accurate. So these are the 2 X's that I got, and the second X is wrong because the end concentration of ions cannot be negative. So our X will be 3.60 times 10 to the negative 5, and if you remember, X stands for the molar solubility, so X is equal to this, and that must mean that our molar solubility for copper 2 chromate is 3.60 times 10 to the negative 5 molar. So remember, if you're lost, feel free to pause the video and copy what I'm doing. So now let's move on. Let's try to figure out what the normal solubility of copper 2 chromate is in pure water. So I set up the same ice chart, but instead I have pure water, so the initial conditions will be nothing since it's pure water and there's no ions in it. And of course, our copper 2 chromate will dissolve, and I solved for X, and it turns out that the molar solubility for copper 2 chromate in pure water is going to be 0.0019 molar. So notice how by having an ion to start with, our molar solubility went all the way down to 3.60 times 10 to the negative 5 molar. These are magnitudes in difference. So this is how the common ion effect works. By having a common ion, you're decreasing the solubility of the salt. Now let's talk about one more thing. This might get confusing, so stay really alert. Selective precipitation is when you want to selectively precipitate an ion out of solution. You choose an ion that easily precipitates with the ion, and 2 ions tend to precipitate out of solution when the salt they make has a low Ksp. So remember, low Ksp means low solubility, and low solubility means potentially ions might want to go back to being solid since there might be too many ions. So let's do an example. Let's say you have 0.1 molar and 0.1 molar of barium and magnesium ions. you need to find an anion that will precipitate with one and not the other first. Let's say you want to precipitate the barium cations first. You need an anion that will precipitate with barium more readily than magnesium. Or in other words, the barium salt that you make should have a lower Ksp than the magnesium salt. So, I found something that does that, and it turns out to be carbonate. The Ksp of barium carbonate is 2.6 times 10 to the negative 9, while the Ksp of MgCO3 is 6.8 times 10 to the negative 6. See how the Ksp for this is smaller? Well, that means that by using carbonate, we can precipitate the barium first in the form of barium carbonate. So, since they have the same I value of 2, you can actually compare their Ksps. Since barium carbonate has a lower Ksp, it is less soluble. This means that once you dissolve enough carbonate, barium carbonate will precipitate first. Once you precipitate all of the barium carbonate, adding more carbonate will precipitate the magnesium. But you want to be careful not to let that happen, because the purpose in the first place was for us to separate the barium from the magnesium, so we only want to precipitate the barium and not the magnesium. So we have to be careful about how much carbonate we add. So let's check out some pictures to clear up some confusion. We have 0.1 molar of each of the cations, and I calculated this, which we will do later, but you add exactly 2.6 times 10 to the negative 8 molar of carbonate in the form of maybe sodium carbonate, and now you have enough carbonate and enough barium to the point where they are at equilibrium. So the Q value for CO32- and Ba2+, when you multiply them together, is equal to the Ksp for barium carbonate. So this means that they hit their limit, okay? Or in other words, they're saturated. Now what about the 0.1 molar of magnesium ions? Well, we know that the concentration of magnesium is equal to the concentration of barium, so that means that the Q for magnesium carbonate is going to be equal to the Q for the barium carbonate. But we know that the Ksp for the barium carbonate is less than the Ksp for the magnesium carbonate, so this must mean that the Q for magnesium carbonate is less than the Ksp for magnesium carbonate, which means that it will not be at equilibrium. And yeah, so basically, don't worry about the other ion for now. Now, what about if we added more carbonate than is permitted? So if we're oversaturating it, that must mean that things are going to start precipitating, and I will read this explanation to show you why that happens. So, adding CO32- will cause the threshold amount of carbonate, which is this number, to be exceeded, and as a result, Q will be greater than the Ksp for barium carbonate. Now, if Q is greater than the Ksp, that means the reaction wants to go backwards now, so ions will now combine to form precipitates instead of the other way around. So the moment you add any carbonate to a saturated solution of barium carbonate, the Q of Ba2+ and CO32- multiplied together will be greater than the Ksp for barium carbonate. And that must mean the reaction will shift backwards and precipitate out some of the barium carbonate to return equilibrium. Therefore, essentially, any amount of carbonate you add will immediately combine with calcium to form calcium carbonate, and this must mean that the carbonate concentration will always stay constant, since anything else you add is immediately react with calcium to form a precipitate. So this actually happens until all of the barium is gone. So like not all of it, but like 99.99% of it, which is basically all of it. Then the carbonate concentration will climb back up again since there's no more barium to react with, and it will hit an equilibrium with magnesium, or the Ksp for magnesium carbonate. Now adding carbonate beyond this threshold for magnesium carbonate will start the process all over again. It will start precipitating magnesium carbonate until the magnesium runs out. Now you don't want to do this if you're trying to separate ions, since you will get both magnesium and barium salt precipitates, and that's not good because they're hard to separate. So, in this picture, you see that by adding a total of 0.1 molar worth of carbonate, which reacts with exactly 0.1 molar of the barium that we had, that will react all of the barium carbonate, and you're left with magnesium. basically, and some carbonate. Now, sorry for doing this, but I meant to say barium for here and barium for here instead of calcium. Alright, so if you didn't get that explanation, hopefully by doing some math, I can convince you. So, here are the Ksps, and we know that we start with 0.1 molar of barium 2+ and 0.1 molar of magnesium 2+. And for this problem, we are going to assume that it's all happening in a 1-liter container. How much carbonate can you add before you hit the threshold or the saturation point for barium carbonate? Remember, saturation, in other words, equilibrium, happens when the Q value or the reaction quotient is equal to the Ksp. So we know that Q is equal to the Ksp in terms of the expression, and it's equal to barium 2+ times carbonate. Now we know that initially we have 0.100 molar of barium and 0 molar of carbonate. So if we multiply these two out, we get that the Q is 0, and since Q is less than K, we know that the reaction will actually go forward. So let me draw a forward arrow. And we know that we start off with lots of solid, and we don't care how much that is. We know that we start off with 0.1 molar of barium, and we know that we start off with no carbonate. So we know that it's minus x, and plus x according to the coefficients, and we get these as our equilibrium concentrations. And we will set that equal to the Ksp for barium carbonate, and doing some math, we get that x is equal to 2.6 times 10 to the negative 8. And this tells us that 2.6 times 10 to the negative 8 molar of our carbonate was dissolved to create a saturated solution at equilibrium. So, over here, we hit the saturation point after adding enough carbonate, or in other words, for every 1 liter, we added 2.6 times 10 to the negative 8 moles of carbonate to make the concentration of carbonate 2.6 times 10 to the negative 8 molar. Dissolving more will cause the excess carbonate to start precipitating with the barium 2+ to get rid of the excess carbonate to maintain equilibrium. So, let's look at the second part and see how that applies. So we are going to start adding carbonate to precipitate out the barium. So, how much carbonate is needed to precipitate 0.1 molar of barium? Well, if you look at the reaction above, it says that for every 1 molar of barium, we need 1 molar of carbonate to react with it to form barium carbonate. So, if we have 0.1 molar of barium ions, then we need 0.1 molar of carbonate ions to react with 0.1 molar of barium ions, because remember how I said that all of the barium will essentially react with all of the carbonate? So we're simply just finding the amount of carbonate we need to precipitate all of the barium out. So, in other words, if the solution was 1 liter, we would need 0.1 moles of carbonate, which by the way comes from any carbonate salt such as sodium carbonate, and this reacts with a 0.1 molar of barium in the 1 liter solution to form 0.1 moles of precipitate. So we used around 0.1 molar of carbonate plus the 2.6 times 10 to the negative 8 molar of carbonate that we started with so far. So if we have 1 liter of solution, then we have to add 0.1 plus 2.6 times 10 to the negative 8 moles of carbonate. So remember, this 2.6 times 10 to the negative 8 moles of carbonate was used to reach equilibrium, but this extra 0.1 moles of carbonate were used to react with all of the barium to precipitate it all out. So, now that we know all that, how much carbonate do we need to reach the saturation point for magnesium carbonate? So far, we've been adding carbonate, and all it has been doing is that it has been reacting with the barium 2+, and the magnesium 2+ was sitting in the background like, when am I going to come into action? So, now it's going to come into action, because after reacting all of the barium 2+, our carbonate concentrations are going to start going up again. So let's read this little story to continue on. Eventually, the system will be at equilibrium when there is so little barium 2+ that the Q for barium carbonate will be super small no matter how much carbonate there is. So this is the point where almost all of the barium 2+ is reacted, or when there is so little that the Q for barium carbonate is so small that it will never precipitate again. So at this point, CO3 can continue increasing as it wants instead of reacting with the barium, since there's no more barium essentially. So it will continue going up and up until it hits the threshold for magnesium carbonate. So the process of precipitation will repeat again if you add enough carbonate. So let's read this question. How many moles or molar of carbonate do we need to reach the saturation point for magnesium carbonate? So let's just pretend that there was no carbonate to begin with, or there's a tiny amount that was left over after it reacted with all of the barium 2+, but we will ignore that for now, and we will consider it to be almost nothing. So we have lots of magnesium carbonate, of course, and we have 0.1 molar of magnesium ions, and we essentially have no molar of carbonate. So we know that it's minus x plus x plus x according to the reaction, and we get the equilibrium concentrations for magnesium and carbonate. So we know the Ksp for magnesium carbonate is that, and doing some math, we get that when there is 6.8 times 10 to the negative 5 molar of carbonate, this is when it reaches the breaking point for magnesium carbonate. It reaches that equilibrium point where you can't dissolve any more carbonate since it reached equilibrium with the magnesium, as calculated here. So we need to add 6.8 times 10 to the negative 5 moles or molar of carbonate, since it's 1 liter and they're the same thing, and 0.1 molar of carbonate to precipitate all of the barium 2+ in the first place to reach the threshold for magnesium carbonate. So if the solution was 1 liter, you would add 6.8 times 10 to the negative 5 plus 0.1 moles of carbonate to the solution to achieve this equilibrium between magnesium and carbonate. So you had to go through all of that just to get magnesium and carbonate to be saturated. Now if you add any more carbonate, the magnesium carbonate will precipitate out. But remember, we don't want that, because if we precipitate magnesium out, we will have a mixture of magnesium carbonate and barium carbonate. So that's very bad, because we wanted to separate them, not to make them more mixed up. So you might have a bunch of questions after that, because honestly, it's pretty confusing, and I was confused when I learned it at first too. But you might be wondering, why didn't the magnesium want to precipitate with the carbonate while the barium 2+ was precipitating? So why did this choose this over this the entire time? Well, there is a simple explanation. Once carbonate reaches the limit and starts precipitating with barium, once you add more carbonate, the carbonate will be constantly consumed and stay about the same until all the barium is essentially gone. Therefore, the concentration of carbonate will remain constant, and this means the Q will remain constant for the most part for magnesium carbonate. We established at the beginning that the Q for magnesium carbonate is equal to the Q of barium carbonate, and the Q of barium carbonate was equal to the Ksp of barium carbonate. And if the Ksp for barium carbonate was less than the Ksp for magnesium carbonate, then the Q of magnesium carbonate will always be less than the Ksp of magnesium carbonate, and this means that nothing will precipitate, since the magnesium carbonate has not reached the saturation point yet. So it will reach the saturation point once all of the carbonate reacts with the barium, and once you continue adding carbonate, it might soon reach the threshold for magnesium carbonate, and you might get to the point where you can actually precipitate the magnesium carbonate out, but that happens after all the barium disappears. So this video, especially the last part, was kind of confusing, so feel free to pause the video, rewind, and do whatever you need to learn the concept of precipitation in regards to selecting one ion over the other to precipitate. So that's all for this video. I hope you learned a lot and have a nice day.